Okay, so it's like we're live. Hello, friends, family, and random internet strangers, and welcome to week 7 of going through code. Um, so this week we got into how larger amounts of memory work from last week, where we started talking about how to store like individual bits of stuff, and then got into how to actually make a computer that you can program. So let's start with the memory pieces. So we're going to jump in to Logisim here for a bit. Okay, so we started basically taking what we had been working with last week and chaining a bunch of them together. So here I have Logisim has little 1-bit register components that we can use. So that's what I'm using here instead of a bunch of flip-floppy circuits. So this is basically, we feed in 8 bits worth of data over here, split it up, feed it into 8 1-bit latches. We have a write that actually tells each of the latches to save what they're seeing right now. Then down here at the end, we're feeding all of the latches outputs into what Logisim and most circuity things anymore call a multiplexer. The book refers to it as a selector. That takes in an address and a bunch of different inputs, and based on the address, it basically picks one of the inputs to send out. So if I go make my second bit here a 1, and I go tell it to look at address number 1, or number 2, or however this thing is. Oh, right, I have to actually write the thing first. Duh. So now this latch, this register up here is now outputting a 1. So when I set the address to 1, I start sending out a 1 from this tiny little piece of memory, right? So in order to scale this up a little bit, next thing the book talks about is taking in 1 bit at a time, figuring out which of our 8 latches to save that bit into, and then sending that out. So we still have our address, we still have our multiplexer, but over here we have, again, what the book calls a decoder, what everything else seems to call a demultiplexer, which does the opposite of the multiplexer. You feed in an address and 1 signal, and depending on the value of the address, it sends that signal out to the appropriate output. So when our address is 0, 1, 0, and our data is 1, and I turn on the write input, it only turns on the third, effectively, write input on our third latch to turn on, which also then sets the third latch and says that we're going to output the contents of the third latch. So if we stick 8 of those together, we now have what the book would call an 8x8 RAM array. So this is an 8x1 chunk of RAM, basically, chunk of random access memory that we can feed in a random address to and send in whatever data we want and get out the data that's stored there. So this is basically 8 chunks of 8 bits of memory that we can address 8 bits at a time worth of, right? So we feed in 3 bits of address, which is enough to talk to 8 different buckets of memory. So I'm going to put that, and we feed it 8 bits of data. We can tell it to save that data. Then when I change the address, it all clears out, except for maybe a thing that I forgot to clear out earlier when I was experimenting with things. Oops. But then when we go back to the original address where I had written stuff, all of my individual RAM cells remember what was supposed to be there and sends the data back out. And we can repeat this pattern over and over and over and over again, both with this individual pattern and making different combinations of individual memory arrays, right? So we can theoretically scale this model up to be however big we want it to be. So I think the book ends up using a 1024 by 8 array in most of its diagrams and experiments. So we have basically 10 bits worth of addresses and the appropriately sized individual RAM arrays. And eventually they all come out and spit out 8 bits still. So, any questions about that part? No? Cool. So, we can take that idea and shove it into our adding machine that we built last week. So, my version here is a little bit simpler than the thing they get to in the book, but it's a start. So, we have one of these 8 by 8 memory arrays here. So, I can go stick in, say, I'm going to put 3 at address 0. I'm going to put a 1 at address 1. I'm going to put another 3 at address 2. And a 4 at address 3. So the book's example basically combined the write and the sort of execute step to actually go do the addition into one clock signal. I broke them out here so it's a little bit easier to follow, and also so I don't end up accidentally overwriting memory data, because I don't have one of those handy control panel things that the book was talking about. I could have built one, but it would be a humongous pain because it's very large. So I separated those out to make it a little easier to work with for now. So right now, my address is at 0, which up here I'm showing the current contents of the memory at this address. So I hit my step button, which actually makes my 8-bit latch over here remember what it's seeing. So I'm adding 3, and the output of this latch is feeding back into my other input in my adder up here. So I'm now adding 3 and whatever the output of this is. So when I go to the next address, which is A1, and execute again, my output turns into 4. I go to my next address and run. I get a 7. Go to my next address, has a 4 in it, and add 4 plus 7 should give me 11, which, since this is hexadecimal, should be a B, which it is. So that is the very, very first steps in building something that we would call a general purpose computer, right? Because last week we had a computer that only did exactly one thing. Well, now we've given it actual memory to remember more than one thing. So from here, the book gets a little bit less detailed. So very key concept from computer science, programming, life in general, this idea of abstraction, being able to kind of ignore all the details, don't worry too much about how the thing actually works. We're just going to kind of go forward assuming that it does. So I don't have a lot of actual circuitry built up for some of this because it'd be messy and gross, and some of the components that I need that are built into the software are kind of not super well documented, so I'd have to go make a bunch of stuff from scratch, which is gross. So I'm just going to go draw some stuff. I'm back. There we go. Okay. So at this point, the next step from here, because right now everything we're doing, we're just adding a bunch of numbers together, right? So the next step the book goes to is, okay, what if we want to be able to add some numbers and then store the result, and then add a bunch of other numbers and store that result somewhere? So that means we need something to be able to actually instruct our little computer and tell it what to do. So right now, at a sort of, if we step back a little bit, think a little bit less about all of the details and work on that whole abstraction thing. We start over here. Oops. Not erasing things. With a, yeah, try that again. Write the word before I draw the box. We start over here with the counter. So this is our, and I'm realizing I'm now drawing outside of my window. Oops. And helps if I write legibly. Okay, so we start with a counter. So this is my address that we started off with. So this is going to walk us from address 0 to address 1 to address 2 to address 3. We keep going. So this right now is feeding into I'm going to call my data RAM. So this is the RAM that we saw a minute ago. This is where we're storing all of these numbers that we're adding together. And this thing feeds into one of the inputs of my adder. The output of that goes into that 8-bit latch, which then feeds back as the other input of my adder. And also lights up some light bulbs. So if we want to be able to do something besides just add stuff over and over and over again, we need a method to actually give it instructions. We need to be able to store and then go back and look at what we want our computer to actually do. So book starts with the simplest answer to this problem, which is we need another chunk of RAM. To store our instructions in. So we go load up our program, our code RAM, with what we want to happen to the matching place in our data. So let's say we want to take two numbers and add them together, but we want to do that twice. So let's say our data, our code. So let's say we have 2, 4, we skip down a ways, we have 3. So in our code, we want to basically just load this first number into our latch down here so we can use it again in our next computation. And then we want to add, we want to take this 4 and add it to what we've already got down here. And then we want to store, we want to take the result that we get from that math and dump it into this extra spot in our memory here. Then we want to do it all again. We want to load. So the idea being that when our little program here finishes, this will be a 6 and this will be a 10, right? So if we want to be able to make something like that happen, we need to make a couple of changes here. For one thing, we need to be able to feed this, the output of our math happening over here, back into our data. So I'm going to attempt to label this. And I should probably label these 2. Close enough. So we can now feed what's coming out of our math into the data in piece of our RAM. And then over here, we need something to control whether to actually save what's coming in here to our RAM or not. And then we somehow need to take our code that we're looping through and tell everything else in here what needs done, right? So don't really get too specific into how to do that. I mean, we know all the component pieces to make it happen, but actually thinking through how to build this control thing and make it work is basically left, for the most part, as a thought exercise for the reader. But we do know a couple things that it's going to do. Like, it's going to tell us whether to turn this right input on or off, right? I really need a tinier eraser. Or just use the undo button. It also might tell us, for example, if we want to build, or we want to have our program be able to subtract as well as add. I'm going to add another input over here. We remember from a couple of weeks ago how most things end up doing subtraction through 2's complement binary trickery. So I'm going to add basically another output out of this control that I'm calling S for subtract. And if we are subtracting, then I want to invert the data that's coming in because I want it to be negative, right? And then I'm setting the carry in of the adder to that S output as well. So we get that extra 1 that we need to make the 2's complement math actually work. What else happens? What else do we need? Don't strictly need it, but something else that might come in handy if we have a piece of data that we just want to load straight into our memory and not go through the mathy portion up here, we might need, again, what the book calls a selector, what everything else seems to call a multiplexer. Over here, so that we can pick between whether our data is coming out of the adder or coming out of the just straight out of the memory. So I'm going to call that that works. So that's another output that's going to come out of this magical control circuitry up here, right? Another thing we probably want to be able to clear things. We want to be able to start over with a new computation. We don't need to keep whatever we had around going on. So we probably need a clear output that goes into our 8-bit latch over here to reset whatever calculations we've been doing. So we can keep going on and on and on like this and adding more features that all get controlled by this control circuit up here. Next thing the book goes into talking to you about is, so we've got all of these lines over here, all of these components down here are 8 bits, right? So they deal with 8 bits at a time. So what happens if we want to add a number together that is larger than 8 bits? So since we have this lovely ability to store the results of our computations now, we can make that happen, but we just need a little bit of extra storage somewhere. So, but kind of brings up these words, sometimes kind of doesn't. Oops, I can't do that and that at the same time. Switch back over here for a second. So, couple important words. Flags in this context is a tiny little 1-bit value stored with a latch somewhere inside of our processing workflow. So in this case, we're going to have a flag that stores whether the output of our last addition or subtraction resulted in a carry, right? This also gets used for, or this concept gets used for a couple of other things where we just need a tiny piece of data that gets stored from one operation to the next. Other important word, very similar kind of concept, is a register, which is why that's what the component is called in Logisim. Basically just a set of latches that sits inside the processor that's used to store larger amounts of data in between operations. Most registers get names so that we can refer to them nicely later. So I'm actually going to rename this to its slightly more proper name. I need more room. So this is the accumulator because it accumulates stuff, right? So I'm going to, over here, draw a little line that's coming out of the carry out. This goes into the, I keep drawing boxes before I finish writing things. It's always a mistake. So this is our carry flag. So this stays over between executions of things so that when we add the first chunk of our multi-byte number, we know whether we need to carry when we add the second one, and on and on and on. let's see what next. Okay. Yes. So next thing that starts complicating stuff. So let's say we want to run some code that has nothing to do with the current position we're at in our data, right? We want to sort of separate our order of our data from the execution of our code and how that's happening. So in order to do that, we need to make our code twice as big effectively. So before, our code was just, we have operations. So earlier I was writing things like add or load or store or even like subtract, right? So all of these end up corresponding to a number that we kind of get to pick. So the book picked, okay, so add is 20 in hexadecimal or 32, right? Or load is 10 or store is 11 or their subtract is 21. So right now, all of our instructions are just this 1 byte value. But in order to make things a little bit more flexible, a lot of our instructions are going to need a second byte, or depending on how big our RAM is, maybe a third or fourth or fifth byte, so that we can decide where we're going to look to see what number we're going to add or where we're going to store something. So in order to do that in our current infrastructure, we need write slightly larger. We need another thing out of here. Gives us our address. And then this goes away. The address. So the address that we're reading out of RAM is now coming from our code, not just from stepping through each position in memory, right? So does that all make sense so far? I'm getting vague head nods. That's probably a good sign, right? All right. So the next point where things get complicated, both because having 2 very large chunks of RAM for things is expensive in the fact that like that's a lot of circuitry to have sitting around, and for the fact that if your code and your data are basically the same thing that lets you do lots and lots of other nifty things later, we're going to erase this, and we're just going to end up with erase more of this stuff because I'm going to need some more room. I'm going to have one, let's put it more over here, one big chunk of RAM, right? So in order for this to work, we need I'm going to move that because I need more room over there. And I'm going to make this smaller because I'm going to need more room over there too. So this is going to just be ER now. So we're going to go back to, for now, stepping straight through to RAM. We're going to add a couple couple more 8-bit latches, couple more registers up here that the output of this will go into. So my example, I don't necessarily need the third one there. Okay, so the way this is going to work, here. And actually, there. This is going to need to feed into here. There. Because sometimes we want to read straight out of our counter, right? Because we're just stepping through the code. Other times we want to read out of somewhere that our code has told us to go look for something, right? Because if we're going to go add a couple of numbers together, we need to be able to go tell it where to add from, right? Then we also need to be able to go load one of our instructions and feed that into our control circuit to tell everything else what to do. And then let's see. Yep, I will need another latch here. Because sometimes we will need data that just goes straight out of our memory and goes into the rest of this circuit down here to be able to actually be mathed on and stuff. And then this is go back up here as our data in. And then we need just a little bit more logic up here to control when each of these 3 latches is actually getting written to, because we don't want all of them being stored all of the time. Otherwise, we're going to end up with memory addresses being sent into our control circuits, or numbers that we're adding being sent back into memory instead of being sent back out here. So we need sort of a secondary counter down here that basically gets fed off of that one. I'm going to call it L, even though I'm using L other places. So this feeds, it's going to be L1, 2, 3. Right. So as the counter chugs along in memory, it's going to feed this other counter, which is deciding which one of these places each instruction gets loaded into. Okay. So does that idea make sense? Ish? Cool. So, kind of to go along with this, because now we are starting to get, again, very abstract, very weird, very far away from actually being able to make this work. I'm going to post something on the website, the link to something I used when I was teaching, which is basically a tiny cardboard computer from the 60s. I know, sounds like a lot of fun, but comes with instructions and stuff to cut out of cardboard or cardstock or whatever. And it's basically an implementation of all of this. It comes with a very simple set of instructions to follow and basically helps you go look at that process and step by step work through how a processor actually chugs through instructions and does things to them, right? Let's see. So the other big important thing that we talk about here is the jump instruction, which I'm not even going to try and start drawing right now. Basically, the ability to jump from one place to another in your code. So that basically just means we need to add another latch or another register in between our main counter and our RAM to go say, okay, this is now where we're at in the code, and we keep going from there until something else tells us to go jump somewhere else. So we need to be able to reset the value in that latch to something else to feed it in to keep everything else moving. Then the last little bit of the chapter gets into basically how this whole structure relates back to like how modern computers are actually work and how they're structured. So again, like we talked about last week, the theoretical model for your computer is we have, so in our case, we have up here, this whole structure is our, we have memory, we have processor, we have our output, and I didn't really draw input anywhere on this particular circuit, but we can kind of just assume that somehow there is some mechanism for getting code and data initially loaded into our RAM in the first place that serves as input. And any other things? It also talks about how assembly works, as in like the programming language that is basically the same as just dumping data straight into your RAM, except using words instead of numbers for everything. So that is about it for this week. Any questions, comments, concerns? I see head shaking, so I'm assuming that's a no. Cool. So, looking at next week, now that we've gone and sufficiently complicated things now. Hey, not what I want. What are we doing next week? So, right now, basically everything we've been talking about, at least if you wanted to go build this, we're still in the phase of like relays, right? So if you actually wanted to go build even like an 8x8 memory array that I was talking about, it would be about the size of my office because, you know, relays aren't small. It'd also take a lot of power and be messy and gross and probably kind of loud. So next week, we're going to talk about shrinking all of this down and some of the historical developments that allowed us to take something that used to be the size of my house and fit it inside of my watch, and how to package all of that together and some of the other things that go along with making things tiny. And then after that, based on reading through things and how the rest of this is going. I'm basically just going to do a real high-level overview of the last 5 chapters because they're pretty high level anyway. So just a quick jump through tour of the last bit, and then I think we will call it done. So we've got another 2 weeks of this, and then we'll be done. So thanks for coming. I'll see you next week.